Today we're going to talk about titrations. And we did titrations last chapter where we did some calculations with things at the equivalence point. But now we're gonna add a lot more detail and we're gonna add a lot more depth. So you'll have a stronger understanding of like how the titration curve is generated and what it all means. So for the first example, which I have here, scenario one, this is an HCl NaOH titration, which we did a lot last unit. So this is your strong acid, strong base. And the reason that I'm picking this one first is that there's no equilibrium. It's all just stoichiometry. Okay, so I'm just gonna show all the math for this one. When we get to the second scenario where there's a weak and a strong, then I'll go through step by step and show you the math for each one. So if I just start with my HCl, okay, I'll be able to get my pH as 1, okay? Now part 2, if I take my 100 milliliters of 0.1 molar HCl and 50 milliliters of my 0.100 molar sodium hydroxide. So I'm picking a point where, I mean, this is a nice point because it's half the amount. And that's a good point for us, which we'll talk about when we get there for the next section. But I can do a Rice end here, and hydroxide ion is my limiting reactant, so I end up with 0.00500 moles of hydronium ion. The volume has changed, so now that I have the number of moles, I need to convert that to a concentration. Okay, and I get 0.033 molar H3O plus, which is a pH of 1.48. Okay, now you'll notice that there's not a huge change between these two, and we'll talk about that as well. Then we get to the equivalence point when the things are present in chemically equivalent amounts, so equal moles of each, which for these two solutions is 0.0100 moles. And we end up with nothing, so pH is 7. Okay, point 4, we've gone now past our equivalence point. And so now we have more hydroxide. So now our hydronium ion is the concentration, is the limiting reactant. We use it all up. We find the the amount of hydroxide ion that's left. We get a final concentration of hydroxide. I know this says H3O plus, but that should be OH minus. Okay. And then I can use the pH plus POH equals 14, and then solve for 14 minus POH. POH is negative log OH minus. So I get 12.3. So this one starts at like 1 something and ends up at 12.3 or higher. Okay. And then we do the last part, same kind of setup where hydroxide hydroniums are limiting reactant. So we use up all the hydronium, we have hydroxide left, we get a final concentration of hydroxide ion, and we can use that to find the pH, which is 12.5. So again, you'll notice between this point and this point, no big change in your pH. So you remember pH curve at the equivalence point for a strong acid, strong base, pH is about 7. Okay, great. So let's do scenario 2. Okay, we're going to add HOBr, so hypobromous acid, and NaOH. So this is very weak, and this is strong. Okay. So, point 1, 100 milliliters of a 0.100 molar hypobromous acid solution. Ka for hypobromous acid is 2.0 times 10 to the minus 9. So we've got initial concentration of 1.00 molar, 0 for these two, goes down by x. And then we're going to use the simplification here, which should be valid because look at the size of that Ka. It's really small. Okay, so now I'll end up with all right, so x is 1.4 times 10 to the minus 5 molar, and that in turn gives us a pH of 4.85. All right, you should be pretty good on calculations like that at this point. Okay, so 0.2 milliliters of 0.100 hypobromous acid plus 50 milliliters of a 0.1 molar sodium hydroxide solution. Okay, so first thing that we got to do is we got to do our Rice N table, the stoichiometry again. So these need to be in moles. So HOBr is 0.0100. OH minus is 0.0050. Concentration at OBr minus is 0 initially. Okay. Hydroxide ion is our limiting reactant. So we get 0.0050. Oh, I forgot a 0 up here. Okay, this is 0, and this will be plus 0.00. Okay, so now I gotta find my concentrations, and these concentrations will actually both be the same. So this is interesting. So this is 0.0050 moles, and our total volume is 150 milliliters. And then we can do a milliliter to liter conversion, 10 to the 3 to 1, and we get 0.033 molar. Now, these OBr minus and HOBr are both going to have the same concentration because they have the same number of moles after this equilibrium. Okay, so now I have equilibrium values of these. Well, I don't. I have the starting points of a Rice EQ table, but we're going to make the assumption and just say that this is going to be our equilibrium value. So then I can use Henderson and Hasselbalch. Okay, now the log, since these both have the same concentration, this is log of 1, which means that this simplifies to 0. So pH equals negative log of the Ka, which is 8.70. So you'll notice that we've actually already had a pretty big jump in the pH, okay? But you'll also notice that at this point, okay, the pH equals the pKa, because these concentrations are the same. So this is actually a buffered solution, okay? And so, like we've calculated and talked a ton about buffered solutions, but here's my weak acid and its conjugate base present in equal molar amounts. Now, the reason that this is kind of not a great buffer is that they're pretty small concentrations, but this would be a buffered solution. So in this phase, we actually resist changes in pH, and I'll talk about that again at the end. Okay, so point 3, we're going to do the equivalence point. Okay, so we're going to do our rice end table, and that is 0.0100 moles. Hydroxide ion is 0.0100 moles. These are both moles. And they're present in stoichiometric amounts, so they both just go away. Okay, so now the concentration of OBr minus is just going to be 0.0100 moles over 200 milliliters. And then milliliters to liters. And that is just 0.05 molar. Okay, now my equilibrium for this one is this OBr minus is a conjugate, is a base, right? So that's going to react with water to make hydroxide ion and HOBr. So that's 0.05, and it's going to go down by x, and we're just going to make the assumption and call that 0.05. Okay, now we have the Ka for HOBr. We're going to need a Kb, right? Because this is a Kb reaction. We don't have this Kb value. So we have the acid ionization constant. We don't have the base ionization constant. So we need to use the identity that Ka times Kb equals Kw. And so Kb equals Kw over Ka. And then we can take this, we can substitute it in for Kb. We get Kw over Ka equals x squared over 0.05. And when you do that, x is square root of Kw times 0.05 over Ka, which equals 5 times 10 to the minus 4 molar. Okay, so pH then for this would be 10.7. Now, we knew from before that if you reacted a strong base with a weak acid, okay, the pH at the equivalence point was going to be greater than 7. Now we can actually calculate what that value is, rather than just saying like, oh, it's greater than 7, it's less than 7. Now we can actually figure it out. Okay, onward, part 4. So 100 milliliters of a 0.100 molar HOBr, 150 milliliters of a 0.100 molar sodium hydroxide solution. Okay, so we're going to start with our stoichiometry. 0.0100 moles. OH minus is 0.0150 moles, and that's just the molarity times the concentration, or the molarity times the volume. There we go, Mr. Ryan. That's good. Let's do this. All right, now HOBr is actually our limiting reactant. Okay, so in our solution, after this thing, we'll have hydroxide ion and OBr minus. But OH minus is much stronger than OBr minus. Okay, so we actually just ignore this, okay, because OH minus is just so much stronger. If you want, you could prove it to yourself, and do OBr minus plus water makes OH minus plus OH minus plus HOBr. And when you calculate the concentration of OH minus generated in that, it will basically be so small compared to the 0.0050 moles of OH minus that we just kind of ignore it. Okay, so now we can find our concentration of OH minus. Over, now we're in 250 milliliters of solution, milliliters to liters, and we get 0.002 molar OH minus. Okay, now that we can find the pH of, and it is 12.3. Okay, and then our last point is going to be basically the same. Okay, and I'm going to do this one very quickly. One of the things that I want to talk about with this is the sort of shape of this graph. So down at the beginning, when we did point 1, this is actually not a very good buffered solution. We know that point 2 is actually like the definition of a buffered solution. So when you do a strong acid, strong base titration, right, you might get something like this. Okay, when you do a weak acid, weak base solution, it actually looks like this. Okay, and the textbook that we're using here has a really good image of a bunch of different pHs. Now, what we'll notice is that in this range here, okay, here's our buffer. Here's our buffered region, where we're adding a bunch of base to it, and the pH is basically not changing. And if you look at like this curve, if you look at the middle of that curve, that's going to be where your pH equals your pKa. Okay, but before, if we go look at like point 1 and we think about between point 1 and point 2, there's such a small concentration of the base initially that we don't actually get good buffering in that region. That's why at the beginning of these, you'll oftentimes see a region where there's a great change in pH when you're adding base in. Okay, but again, you'll notice that they all have equivalence points that are like the amount of the base that you add isn't going to change, but where the equivalence point happens changes based on what acid, the strength of your acid. So I might just have you like pick an acid base combination and just do some calculations for them. Okay. You've done most of these calculations before. It's just kind of putting all this stuff together.